So some of the ways of doing this are data-driven methods. So one of the methods, so GBM, so the geometric Brownian motion, which was, incidentally, it was some guy called Brown came up with it. And what he had noticed is that bacteria was, and bacterial growth was just moving at this really random pattern. And what he saw is that it was he became then known as a random walk. And that's when you have no knowledge of what is going to come up, but you do know what the uncertainty is around a variable. So it's a stochastic process. And it really works well for things such as stock price, interest rates, exchange rates. Could also work for bacterial growth, as Brown had discovered in the early 20th century. It basically looks at fractional changes in the variable between periods. So that month-to-month change that you might look like, well, you would make that stochastic, so it becomes a normal distribution. And since they're uncorrelated, they're all independent, and what happens in period 3 has nothing to do with period 1 or period 2. It is an independent, but it is a fractional change from what happened. So I have some example models that we'll look at in a few seconds. So autoregressive. So it sounds kind of like an interesting word, Autoregressive means it's a stochastic process for that you can look. It's a stochastic process that applies white noise error. Okay, it looks at the weighted sum of the previous values, and it gives you these very interesting patterns. So if we were to adds white noise, things that this is often used in the financial area. Some of the models that we're familiar, we've talked about actually. So you have the actual autoregressive models, you have moving average models. Then you can combine them. So you can have autoregressive moving average, autoregressive integrated moving average. So that's what Box-Jenkins came up. Then you have ARCH, GARCH, EGARC, and APARCH. So those are heteroscedastic models. Again, just a fancy word to talk about stochastic. And again, these models apply to the returns. Here are some formulas that you could look at. So you have GBM if you wanted to replicate these in Excel. So you have your mean and your standard deviation at a different period at said time of your variable at a said time. You have the the Cox-Ingersoll model, the Gompertz curve. Here's the mean reverting stochastic here. So you can see that they use natural log values, and you can correlate them. So, and that you would do by picking the mean of the previous. So now I'm sure you all have been waiting for this. So let's take some time and actually get into a correlated time series model. So there's a really interesting feature that we have access to in at-risk, and it is the correlated time series. So what I'm going to do is I'm just going to pull up the appropriate model, and I'm going to switch it over here. So just bear with me. And here it's loading. Okay, checked everything out. All right, I'm going to switch this over, and here we go. So tell me if you see this, Jameson.
Yes.
All right, excellent. And I'm just going to go in the background, and I'm going to close some of the other models that are running, and we'll bring those back up in a quick second. So you're getting a sneak preview of what we're going to be doing here. Okay, very good. So hide these. So what we did is we went to the Canadian Census Bureau, and we got some historical data on various commodity indexes. And we're just pulling up the entire data, and we're going to go over here. And what we had in this is that it's from 1971 till July 2011, we had the progress of an index of these commodities. So for energy, mining, forestry, agriculture, these actually happen to be true numbers. And for the sake of the exercise, we created a rolling volatility calculation, as you can see over here, using these very nice spark lines, that for the volatility against these log returns on a 12-month rolling basis, 36 and 60 months over here. So that's the first thing to give you a sense of the data. So let's look at how the model is constructed. It's a very straightforward model, and what we did is we did a very simple exercise where we did a curve fitting. And we came up with a curve fit using, I think I made it disappear, but we used a polynomial which had an 80% correlation to it. And then we applied a normal stochastic process to it. So it's using the volatility and the mean numbers to generate this. So we have the mean values over here, and we have a 12-month volatility number over here. So how would this look? So if we made these numbers dynamic, what we could see is that by hitting F9, we can see that we have all these various market scenarios with the returns being forecasted per. And that has enabled us to create the following. So what we did is we wanted to create a model to figure out if we took $1,000, where would we invest that money to get the highest return over time? And that's going to be the topic of discussion. So if anybody wants to put up now, Jameson, is it possible to get a show of hands here?
Oh, we can have our people just type in chat, and I can.
So there's no way to get a show of hands, right?
Yeah, well, there kind of is. It's probably as good as the right board feature.
Okay, so because what I'd like to get is a sense of who thinks which commodity. I'd like to get a vote on which commodity people think will give them the highest return.
Mm-hmm. Oh, we'll take a poll, everybody. You can just type in what your answer is. I'll kind of tabulate and read them to Eric, and then we'll all know. But yeah, that sounds good.
Okay, so while we're doing that, I'll just finish. So what we did. So we took $1,000, and then we took that and we applied it against the various returns. So in this case, we're looking at the 12 months, and so we have the 12 months going. So we have one vote for energy. Okay, that's good. Anybody else? No?
Oh, we've got energy, agriculture, and we've also have mining.
Okay, so one for mining.
Energy. So our majority is energy. We have quite a few mining and 2 agricultures.
Okay, so we'll consider I guess the sample size will tell us that more or less energy is the predominant one. So what we're going to do is we're going to run this model for 5,000 trials for one simulation, and we are going to see which one is the winner. Now, you might be in for a surprise, Jameson, because I corrected a few things in the model since we went.
Oh, okay. Yeah, we did this 2 days ago.
Yeah, so I just wanted to make sure that what we were doing was sound.
Okay.
So one of the other things that we did while this is running is that there is a method. Okay, so before we get into the answers here, At-Risk offers a really interesting method for what they call a correlated time series. So one of the things that we did, and I guess I'll wait till this guy's done running and I'll just talk through it, is that we did a correlation matrix. So we took the historical data and we went back 5 years, all the way to 2006, and we looked at the monthly data. And we did a rank correlation, which we have in this worksheet, to figure out what was the relationship between those variables. So we took the relationship of the previous 5 years and decided that that would maybe be, at least for the sake of this discussion, an appropriate correlation matrix for the next 5 years. And what the correlated time series tool will do is that it will go through each line in your data set. So it'll go through line 1, line 2, line 3, and it will apply that correlation matrix to each line between the variables. So now what you have is you've explicitly how you have correlated the time series. However, it is important to note that the underlying values that you would use to forecast, so the volatility, the trend, all of it needs to be done up front. However, once that work is done, in a very artisanal way, you can come up and do this. So to come back to our correlation matrix, we'll just hide this for a second. We took that, and this is the correlation matrix we generated. And when we came to the returns, we just said, okay, you're going to take these correlation ratios and you're going to apply them through each row. And it went pop. And then you would even see it pop, pop. And so that should give you a sense of how it's doing it. And if we ran this model uncorrelated, we would have a probably less volatility in there. Anyways, so let's look at our answers. So energy, so let's see. So let's start with the first one. So energy. And we go to the browse results. And what we can see is that we have a mean of 1,100, and 161 with a standard deviation of 50. Okay, not bad. And the minimum over here means that we might have lost a little money. However, it would have been a pretty safe bet that there was a 99.99% chance that you would probably not lose any money investing in energy. Okay, so that's interesting. Okay, now let's go look at mining. So now with mining, look at this. We have a mean of 1289 with a standard deviation of 40, which means that we would have a much higher, it's a less risky investment, and the minimum, our guaranteed minimum is $150 more, so 15% more than if you had invested in energy, and it is less risky. So going on here, now if you had invested in forestry, you might have lost. You might have had a slight probability of losing some money over here. So let's see how much that would be. So you'd have a 3% chance at a loss and a 97% chance at making more money. However, your mean returns are barely 4%. But it's not risky. And then lastly, we have agriculture, which, believe it or not, is almost comparable to mining. And therefore, you have a mean of 1,239 and a standard deviation of 39. So the two best investments are mining and agriculture. And intuitively, just like most of you, when I built this model, I felt that energy was probably the one, but actually energy is the most volatile. But over time, and this speaks to how we understand and we envision the world, we tend to forget that there is a food crisis. I don't want to sound like the mother of motherhood, but we have a food crisis, and really the truth of it is that over the last couple of years, food prices have been increasing around the world at a steady and incremental rate. And for those of us, for example, in North America, we don't notice these things up front. And then, the idea of agriculture being, a solid investment over the next couple of years, had never dawned on me. And maybe it hadn't dawned on some other people. I digress. Now, some of the other cool things that we can do, in terms of charting, is that we can pull up what we call a trend chart. So to do a trend chart, so we're going to browse the results and we're going to see, so over here and see if we can pull it up. Here it is. So summary trend. And to build the trend chart, it's actually really easy. You just highlight the range and Shazamo. So in here, agriculture seems to be having, a fairly steady, it seems to have a very steady trend. These are the mean values. And the way you would interpret this, okay, is that, and I wonder, why did that not come up a little more hazy than that? Anyways, I have other examples of time series that we could look at, but the value is going to be anywhere within here. I know why. Because when we did this, we projected using a linear trend, and using the linear trend, we feel that the value could be anywhere between these two green bars, nine times out of 10. And here is one, since it's a normal, it's plus or minus 66%, we think that the value will be in here. But we do feel that it is a linear trend, and that linear trend fitted at, if you ever get an R-squared value, the easy way to calculate that is that if you take the calculator, and we had a point, I think it was like a 0.569 R-squared, if you take the square root, that's a 75% correlation with that linear trend. So we'll just get rid of this and that. And another way you could look at it is using a box whisker plot. I have some interesting slides where we can look at other variations of this. So that is the correlated time series. Okay, so I see that we have a question from, I hope I won't mispronounce your name, but Yahya El Hassan. So may you show us how you forecasted the data in the first place? Yes, I'd be delighted to do that. This, of course, we didn't look at doing something extremely sophisticated for them, but let's see if I can give you a very simple example. So over here, we have the forecast data. So we used we did a curve fitting exercise. I did delete some of these charts, but I will explain the process. And curve fitting is not necessarily the same as forecasting, but curve fitting is a very important tool for the forecaster. So what we have here, and I do want to caution people, when you do a curve fit, it might look really good against historical data, but it is not necessarily, and I will mention this, it's not a good predictor necessarily to say that this is the pattern that will keep out over time. So what might have been true for the last 40 years might not hold true for the next, 5. So when we did this, you take a time series and you can add a trend line. So I'm going to add a new trend line and we'll take a linear one for the energy series, and we will ask it to display the R and the equation. And the R-squared value is what we did with. So if we were looking at a linear, what we would know is coming back to our calculation method over here. We would take 0.4989, and what R-squared tells you is that it's accounting for, this line is accounting for about 50% of the movement. And if we wanted to get the correlation, or what would be the equivalent of a Pearsonian value of this, you take the square root, and you would say that this line kind of correlates at 70%. Let's get rid of this. So this is what we did. So we actually used this for the other three. We did this process. So I'm just going to delete this, and I'm going to reapply it. Format trend line, and I will display the R-squared. And what we could see is that using a polynomial, and I believe this one is a fourth degree polynomial, we get an R-squared of 0.76. So this very, very much correlates or accounts for the behavior. So we did this for all the series, and using these very interesting functions, we calculated using Excel what these values would be, and we applied them here. There are other methods we could have used, but we just wanted to get a sense of what we were doing. And using these values, we then calculated out what the returns would be, and this is what is populating this over here. So these are the mean values for growth that we have projected, and then using the latest volatility numbers, we applied them uniformly across, and then we auto-correlated them by series. So we did not. We didn't use any. We could have done some smoothing or some deseasonalizing. We did play around with stats tools a bit. If we have time, I'd be delighted to show it. However, you do need to have some sort of indicator of where your forecast is going when you do smoothing, right? Anyways, please show us the detail. What detail are you referring to, Yaya? Because I have just a few more minutes, and after that I'll have to keep back to our presentation, and we can always talk about these offline. However, I would like to try and answer this as best as possible. Yes, we used only the historical data, Yaya, is over here. So if we come back to this data, this is which comprise So if we didn't pull out the dates over here, but we have them in our other model, we do have the enumeration of the periods. So to get our general trend, we got it using a linear, and using that, we're going to apply variability to that base estimate. That's how we did it, and then we did it using forecasted returns and assigning the volatility based on the last 12 months, and we carry that forward. We could have done the same thing. Probably it would have been a little more appropriate to use the 60-month volatility numbers instead of the 12 months. So I hope that answers your question, Yaya. The point of the exercise is to demonstrate how we use the correlated time series, and basically an explanation of how you would apply the returns approach to volatility on a curve. So moving, hopefully that will have answered the question. If anybody else has any questions, please feel free to send me a chat. So this is, and here my pleasure. And over here, just so we know, here are the dates. And by the way, a really nifty feature to clean up a model is to use what I referred to as the grouping function. So there you go. Okay, so moving along, going back to our PowerPoint. Some of the probabilistic graphs that we have, as we mentioned, a trend chart could look very different than just a straight line. That's why in our previous example we used, whereas here we had not. We used another method, and with at risk you can look at it both using this and the box plot.